There is a material that costs less than $1 for enough to solve this problem completely. You already have it in your kitchen drawer. You shape it into a specific curve. You position it behind your router's antennas, and your Wi-Fi signal strength in the rooms where you actually use your devices increases by up to 55%. Not in the spec sheet. Measured in a peer-reviewed study from Dartmouth University. The dead zone in your bedroom that has been dropping video calls for 2 years, the corner of your house where Netflix buffers every single time, the weak signal in your home office that forced you to buy a signal extender for $40, all of them solved with $1 of aluminum foil shaped correctly behind your router, in 60 seconds, without touching your internet plan, without calling your provider, without upgrading your equipment. This is not antenna folklore, it is radio wave physics. The same electromagnetic principles that govern satellite dishes, radio telescopes, and military radar systems govern the 2, 4, and 5 gigahertz signals coming from your home router. A parabolic reflective surface positioned correctly behind a radiating element does not create new signal. It captures signal that was already being broadcast in the wrong direction and redirects it precisely toward your usage area. Signal that was being wasted on the outside of your house, absorbed by concrete walls, radiated into the attic or the floor, is recaptured and redirected. You are not amplifying, you're aiming. And aiming costs $1 of aluminum foil. Then someone in a corporate boardroom did the math. The home networking equipment market generates over $20 billion annually in the United States alone. Wi-Fi extenders, mesh network systems, upgraded routers, and signal boosters represent a multi-billion-dollar product category built on the premise that weak signal requires hardware purchases. A $1 passive reflector that meaningfully improves signal distribution in the majority of single router home environments does not generate hardware revenue. And telecommunications companies, which profit from consumers upgrading their service tier to compensate for perceived speed issues that are actually signal distribution problems, have no financial incentive to explain reflector physics to residential customers. Welcome to Forbidden Fix. If these stories matter to you, hit subscribe and the bell. This is where we dig up what industries spent decades trying to erase. To understand why a curved piece of aluminum foil meaningfully improves Wi-Fi performance, you need to understand how your router actually broadcasts its signal and why most of that signal is being wasted every second your router is running. Your home router broadcasts radio waves at frequencies of 2, 4 gigahertz, or 5 gigahertz. These are electromagnetic waves, the same physical phenomenon as visible light, just at much lower frequencies. Like light from a bare bulb, an unmodified router antenna broadcasts in a roughly omnidirectional pattern. Not perfectly spherical, but radiating in all directions simultaneously. The antenna sends signal upward, downward, through all 4 walls, through the floor, through the ceiling. It is broadcasting toward your neighbor's house. It is broadcasting toward the street. It is broadcasting into your attic. The vast majority of the signal radiated by your router never reaches any device you own. It is absorbed by walls and floors and transmitted into space where it serves no purpose. A parabolic reflector works by intercepting electromagnetic radiation coming from a focal point and redirecting it into a concentrated beam. This is the principle behind satellite dishes, which concentrate incoming signals to a central receiver, and behind flashlight reflectors, which take light radiating in all directions from a bulb and project it forward as a directed beam. Applied to a router antenna, a curved aluminum foil reflector placed behind the antenna intercepts the signal being radiated backward, toward the wall your router sits against, and redirects it forward toward the living space where your devices are located. In 2012, researchers at Dartmouth University's Computer Science Department, in collaboration with South Korea's Korea Advanced Institute of Science and Technology, published a peer-reviewed study in which they built what they called a Wi-Fi router reflector, using household aluminum foil shaped over a simple printed template. The study measured signal strength at multiple points in test environments, with and without the reflector. Results showed signal improvement of up to 55% in targeted directions and simultaneous reduction of signal in directions where privacy or interference were concerns. The paper was published in a legitimate academic venue. The methodology was sound, the results were reproducible, and the practical implication, the $1 of aluminum foil meaningfully improves home Wi-Fi distribution, was covered briefly in technology media and then disappeared from public conversation. Before I go further, this video covers the foil reflector technique and 2 complementary positioning strategies. Inside the Forbidden Fix vault, I've compiled complete home networking optimization guides covering router placement physics, channel optimization to avoid interference, antenna orientation principles for different router types, quality of service, configuration to prioritize your most important devices, and the exact techniques that network engineers use to optimize signal distribution in commercial buildings. The link is in the description. But stay right here because the Wi-Fi hardware industry's pricing model is built entirely on a single emission. Military radar engineering has used parabolic reflector technology since World War II. The principle was well understood before home Wi-Fi existed. Radio astronomy uses parabolic dishes to collect signals from billions of light years away by concentrating them to a single focal point. Amateur radio operators have built parabolic reflectors for antenna gain for over 70 years using mesh, sheet metal, and foil. The physics are completely established. When Dartmouth published their consumer application of this principle in 2012, they were not discovering new physics. They were applying century-old physics to a new consumer context. The telecommunications industry's response to this research was silence. No consumer guidance. No router packaging update. No ISP newsletter. Nothing. Because a customer who solves their Wi-Fi problem with aluminum foil does not buy a $40 signal extender or upgrade from a $60 plan to a $100 plan, believing that more bandwidth will solve a signal distribution problem. It will not. Bandwidth and signal strength are different variables. You can have 100 megabits per second available from your ISP and receive 3 megabits per second at your device if the signal path between the router and the device is attenuated by distance and obstacles. The hardware and service upgrades do not fix signal distribution. The foil does. If you have made it this far, you understand more about radio wave physics and router optimization than 99% of consumers who have bought signal extenders, mesh nodes, and upgraded service tiers for a problem that costs $1.60 to address at the source. Subscribe and share. One share is one more person who does not buy a $40 Wi-Fi extender they do not need. Here is exactly how to do it. Step 1. Identify where your signal is weakest and where it is strongest. Use your device's Wi-Fi settings to check signal strength in different rooms. Your router is broadcasting toward rooms where you do not need signal just as strongly as toward rooms where you do. Step 2. Cut a piece of aluminum foil approximately 16 inches wide by 10 inches tall. Standard kitchen foil works perfectly. Step 3. Shape the foil into a parabolic curve. The simplest method is to find a cylindrical object of approximately 6 to 8 inches in diameter, a large pot or mixing bowl, and curve the foil around it, then remove the cylinder. The foil should hold a curved shape resembling the cross-section of a satellite dish. Step 4. Create a stand for the reflector from cardboard, wire, or simply prop it against the wall behind your router. The reflective concave surface should face the router antennas. Step 5. Position the reflector directly behind the router's antennas with the concave face directed toward the antennas and the opening of the curve facing the direction of the rooms where you need signal improvement. For a single antenna router, one reflector is sufficient. For multi-antenna routers, create one curved section per antenna. Step 6. Open your device's Wi-Fi settings and check signal strength from the rooms where signal was previously weak. You should see a measurable improvement of 10 to 50% depending on your specific environment and router position. Step 7. 2 additional optimizations cost nothing. Elevate the router to approximately 4 to 5 feet above floor level. Radio waves at 2, 4, and 5 gigahertz propagate better when broadcast slightly downward from above the primary usage height rather than at floor level. And ensure the router is at least 3 feet from large metal objects, including file cabinets, refrigerators, and metal shelving units, which absorb and scatter signal. Total cost, $1 in aluminum foil. Compare that to the $40 extender or the $40 monthly service upgrade. I need to be honest with you. The aluminum foil reflector produces its best results in specific situations. It is most effective when your router is positioned against a wall with the signal needing to reach rooms on the opposite side of the router. In this configuration, the reflector redirects otherwise wasted backward signal toward the target area. If your router is already centrally located in an open space, the signal distribution is already relatively efficient and the foil improvement will be more modest. In homes with extremely thick concrete, brick, or plaster walls with wire lath, Wi-Fi signal is attenuated by physical material properties that no passive reflector can overcome. In those situations, a router placement change or a wired access point is the correct solution. The reflector also works differently across the 2 frequency bands. At 4 gigahertz, the longer wavelength signal penetrates walls better but carries less bandwidth. At 5 gigahertz, the signal carries more bandwidth but attenuates more quickly over distance. The reflector benefits both, but is proportionally more effective at 5 gigahertz where directional gain has more practical impact. Your parents had one telephone in the hallway, one connection point for the whole house, and when they wanted to talk to someone, they walked to the phone. The idea of connectivity in every corner of every room was science fiction to them. Today, the telecommunications industry has built a multi-trillion-dollar ecosystem around the expectation of seamless connectivity everywhere. And when connectivity is not seamless everywhere, the solution offered is always more hardware. Higher tier service, more equipment, more billing. Not a piece of foil shaped around a mixing bowl. Not 3 minutes of router repositioning. Not a free firmware update that enables the channels your ISP locked for traffic management. The problems are real. The solutions are cheap. The industry prefers expensive ones. Subscribe and share. Every share preserves what they tried to erase. The next vault opens soon, and what is inside might explain how $1 of powder destroys an entire ant colony overnight without a single toxic chemical in your home.